Hello, and welcome to this recorded e-learning on basic FPGA architecture for the Virtex-6 device family. My name is Frank Nelson. I will be your instructor for this module. This module introduces slice and I/O resources available in Virtex-6 FPGAs. This basic FPGA architecture module limits its scope to discussing the slice and I/O resources. Please note that there are also corresponding memory resources and clocking resources recorded e-learning modules available as well. If you are new to FPGA design, this module will help you target the appropriate Virtex-6 device resources. Understanding the architecture resources is essential if you are going to build a successful FPGA design. The architecture resources are designed to create a fast and efficient FPGA. This module is part of our Essentials of FPGA Design course. We recommend that you take time to attend this course to learn all of the critical design considerations you must make when targeting any FPGA device. After completing this module, you'll be able to code your register resources so your design will have fewer control sets and be able to run at a higher system speed. You'll also be able to avoid the most common coding and design mistakes that reduce device utilization and system speed, and anticipate how your design will map to the FPGA resources in Virtex-6. The objectives of this module are that you'll be able to describe the CLB and slice resources available in Virtex-6 FPGAs, that you'll be able to describe flip-flop functionality and its limitations, and be able to anticipate building proper HDL code for Virtex-6 FPGAs. All Xilinx FPGAs contain essentially the same basic logic resources. Slices, which are grouped into configurable logic blocks, or CLBs, contain combinatorial logic and register resources. As you can see from this picture, there are a lot of CLBs on this die, while each device family is offered with a different number of CLBs. Determining which density is right for your application often requires you to at least synthesize your design before choosing an appropriate density of FPGA. Only with some experience can you properly estimate how many slice resources will be necessary for your design without at least synthesizing the design first. The slice resources are the most essential and fundamental to an FPGA design. They include LUTs and registers. LUTs are built to create your combinatorial logic resources. Each has an associated register with it. The LUTs and registers are grouped into slices, which also have other dedicated resources. Besides LUTs and registers, slices also have carry logic resources, which are designed to implement arithmetic logic functions with high speed performance due to the dedicated carry chain, which runs vertically in columns from one slice to the next. The implementation tools select an appropriate routing that may include different kinds of routing resources. The solution that is routed is designed to try and meet your timing needs. To do this, it is important that you add timing constraints with the ISE design suite so you can communicate your timing objectives to the implementation tools. This will allow the software to choose the most intelligent routing solution to meet your needs. In fact, the mapping and placement of logical resources is handled by PAR, the Placement and Routing Utility. In Virtex-6, all routing, besides the carry logic resources, is routed through the switch matrices. While understanding the interconnect structure is seldom needed, this diagram is meant to describe the population between slices and CLBs. You see, in between each CLB is a switch matrix which is designed to connect to other switch matrices as well as the neighboring CLBs. The possible interconnects are called PIPs, or Programmable Interconnect Points. Please note that proper use of global timing constraints, which are explained in the Essentials of FPGA Design course, are going to be required to communicate to the tools your timing needs. Now, combinatorial logic is stored in lookup tables or LUTs. Lookup tables are also sometimes called function generators. The capacity of a LUT is limited by the number of inputs, not by the complexity. So delay through the LUT is constant regardless of what logic function is being performed inside. Each Virtex-6 slice contains a 6-input LUT that can also be broken into two 5-input LUTs. This allows the resource to be broken down if necessary to assure maximum device utilization. Every customer must understand the input limiting nature of LUTs. Because many customers are used to building with ASICs, it is important to understand that the HDL code you write needs to be optimal. This is because ASICs are faster than FPGAs, and it's much easier to get good speed from an ASIC with suboptimal code. This is highlighted when you consider what you would get if your combinatorial logic had 7 inputs. Because the LUT has 6, your synthesis tool would be required to add a second LUT in series with the first. This would then dramatically increase the delay associated with this path and cut the maximum frequency possible. Also keep in mind that if you're trying to design the maximum speed quoted in the device datasheet, you have to remember to limit all of your delay paths to 1 LUT or 1 logic level. This is not typical, but some customers do it by extensively using pipelining and by minimizing their combinatorial logic. The Designing for Performance course discusses pipelining. Every customer that builds his or her first FPGA inevitably struggles to get optimum speed because they're not using optimum HDL code. I recommend you listen to our HDL coding style RELs so you can be as successful. Xilinx also provides the Xilinx Synthesis and Simulation Design Guide at support.xilinx.com for your reference. It includes terrific coding examples and detailed design recommendations. Each CLB contains 2 slices. From this diagram, you can see that each slice has 4 LUTs, 4 flip-flops, and 4 flip-flops that can also be programmed as latches. We added the additional registers because the LUTs can be broken into 5 input LUTs, and this should help designs get more logic out of the FPGA design. The carry chain is supported on 4 of the 8 flip-flops. There are also dedicated muxes which can be used to build larger multiplexers and save LUTs so your system can get higher speed. In this diagram, we see a number of muxes used to connect the LUTs together. Each slice contains 2 F7 muxes that groups the outputs of 2 LUTs and can create an 8-to-1 multiplexer. Each slice also contains 1 F8 mux that combines the outputs of the F7 muxes and can thus make a 16-to-1 mux. The mux outputs can drive out of the slice or connect to the available flip-flop latch. These dedicated multiplexers are used to improve the speed of large multiplexers and save LUTs for other purposes. The reason that these multiplexers improve the speed of the design is because there is dedicated routing between the multiplexers that are low fan-out and fixed between the logic resources. It is also fast because the dedicated multiplexers are faster than building the equivalent logic just with LUTs. What is most important to remember is that each of the dedicated resources has an intended purpose of saving LUTs and improving the speed of your design. Also be aware that if you are going to code for a large multiplexer, you code with a case statement in your HDL. This is required for inference of the dedicated hardware mux. Carry logic is a dedicated hardware resource that improves the speed of arithmetic functions, such as adders, accumulators, subtractors, and comparators. From the diagram, you can see that the slices are grouped into one carry chain. Please note that carry logic will propagate the carry signal vertically upward. This is important to note because most designs use carry logic extensively, and by using it, the least significant bit should be placed at the bottom of the carry chain. Likewise, when carry logic is used, bit ordering should be followed by the designer, with the less significant bit being placed beneath the more significant bits. Each slice has 4 flip-flop latches and 4 flip-flops. The difference between them, besides their programmability as a latch, is that the flip-flop latches, seen here labeled FF/L, can be driven by the LUT, carry chain, or the wide muxes. Conversely, the flip-flop can only be driven by an O5 input, which can come from the 6-input LUT when it is used as 2 5-input LUTs, or from a separate input to the slice. These limitations are not as much of a big deal. In the end, if you're building lots of lower input functions that share inputs, as is required to have the 6-input LUT broken into 2 5-input LUTs, you should end up with the flip-flops being used quite a bit, and this will aid your pipelining and improve the speed of your design.